All right, so today it's about arithmetic sequences. And the first thing we have to do is we have to look at a sequence and help first ask ourselves, is there a common difference? What do we notice about these particular sequences? So the first one, what's our common difference? 3. So an arithmetic sequence is a sequence whose consecutive terms have a common difference. In other words, we're adding the same thing each time. That's the reason for the name arithmetic. So we notice that there's 3 as a common difference in that particular sequence. What's the common difference in the second one? 4.5, positive 4.5, negative 4.5. Okay? So we have to be careful. If it's decreasing as it's going along, then we know it's a negative, and if it's increasing, it's a positive. Or you can take 95 and 5/10 minus 100 and get 4.5, or 4 and 5/10. All right, questions on these? All right, not too bad so far. All right, the next piece then is that we want to come up with an explicit definition for an arithmetic sequence. So yesterday we saw that it was a little tough to come up with these. The recursive ones were not so bad, but the explicit definition was a little bit more difficult. So let's kind of think about what's happening here. So first of all, they're going to say that if you want the nth term of any geometric or any arithmetic sequence, you need to take d times n plus c, where d is the common difference and c is the first term minus the common difference. Now, that's suddenly two formulas to think about and be able to remember. Okay? I have a better option for you. Okay? So let's think about what's happening here. I like to think of these as like something like a linear equation. Okay? Linear equation of y equals mx plus b, your slope y-intercept form. Okay? Notice the parallels. We have a number is equal to something times a number plus another number, right? So our common difference is similar to our slope, and our c is similar to our y-intercept. Okay, so far so good? Okay, so let's see what happens when we try to write the explicit and recursive forms for that sequence 5, 8, 11, 14, and 17. Okay, so let me kind of draw that parallel to that line. So if we are in our first term, a sub 1, we're up here at 5. Our second term, a sub 2, is up here at 8. Our third term, a sub 3, is way up here at 11. A sub 4 would be at 14. Okay, so do you notice something about these? It forms that line, right? So there'd be a 14 up here somewhere too. Okay, I went a little crooked, but you got the idea. So in order to find that equation of that line, we would want to know what is the rise over run, wouldn't we? Okay, well, we're going sequentially every term, right? So the run is always going to be 1. The rise is always going to be that common difference. Does that make sense? Okay. So if I want to find out the b of my line, I need to go down how many? 3 and over 1. And that would be 2. That would be my common difference. Okay. So when I think of writing an explicit formula or explicit definition for an arithmetic sequence, I simply say a sub n is equal to my common difference times n plus, and then I ask myself, what would it be one step back? 2. And so when I move one step back and find my 0 term, that's what I add on to the end. Make sense? You can draw the parallels between that line and the equation of a line and this explicit definition for an arithmetic sequence. You have less to remember and memorize. Yes, sir. Yep. Yep. And so let's say that we wanted to find the 50th term of this now. We would simply say a sub 50 is 3 times 50 plus 2, so 152 would be the 50th term. Make sense? Okay. All right, that's an explicit definition of an arithmetic sequence. Now we need to come up with the recursive form. And we figured out yesterday that recursive was a little easier to do. Because what do you always start with a recursive formula, or recursive definition? A sub 1. So we define a sub 1 as our first term, 5. And then we need a second part to this definition. We say a sub n, right? You want to get a sub n, what do you have to do? Take the previous term plus, what's our common difference here? 3. So if I want the second term, slip a little 2 in for n, then the second term would be the same as the first term plus 3. And the third term would be the second term plus 3. And the fourth term would be the third term plus 3. Okay, now let me show you one more way that this can be written, and you can write it either way, and your book is going to interchange them. Sometimes instead of saying a sub n, they say, hey, if you want to generate the next term, then that should be the previous term. So what would the previous term from a sub n plus 1 be? A sub n plus your common difference. Okay. If you want the next term, take the previous term and add 3. They both say the same thing, just slightly different notation. Make sense? So you can write either one, and your book will use them interchangeably. Questions on this one? All right, here comes the next piece then. So I've got 4 things for you to do. For this particular arithmetic sequence, we want to first of all find the common difference. Then we want to write the explicit definition. We're going to find the 10th term. And finally, we're going to come up with the recursive definition. Okay? So easy part first. What's the very first thing that we know? Common difference is 7. Okay, so part B says now let's find that explicit definition, so let's practice that. How do we start an explicit definition? A sub n. So our common difference is 7 times n. And then we got to figure out what that previous term was, right? Exactly. If we take 7 away, we're going to get a negative 5 up here, right? So plus a negative 5 or minus 5, same difference. So part C says, let's find the 10th term. So if I want the 10th term of this particular arithmetic series, arithmetic sequence, what are we going to do? Everywhere we see the n, we put in 10. A sub 10 will be 7 times 10 minus 5, which is 65. So that definition is very, very handy when it comes to finding a particular term. And finally, part D, we want the recursive definition. How do we start every recursive definition? A sub 1 is 2, and a sub n, if you want to use a sub n, that's going to be a sub n minus 1 plus 7. Take your previous term and add 7. You got the next one. Questions on this one? Am I getting easier? Make more sense? Okay, here comes the next. So now we're in this box, and we're saying that the 8th term of an arithmetic sequence is 25, and the 12th term is 41, and we're supposed to write the first 5 terms of the sequence. So what shall we do? What shall we try? Okay, so it would be nice if we had an explicit formula. In order to get that explicit formula, we know that a sub n will be our common difference times n plus our term before our first term, right? So now what? Okay. All right, so you could do this. Okay, systems of equation. We know that the 8th term is 25. And we know that the 12th term is 41. And you could do a systems of equations like this. Make sense? Solve systems of equations in that manner. That's one way of doing it. Okay? What's another thing we might do? We said arithmetic sequences are kind of like lines, right? Absolutely, you could. So that's one way of doing this, okay? But let's think about another thing really quick. Actually, we want to do a couple different things. So we don't know the first term, right? Or the second. We're going to try to find these. The third, the fourth. We don't know the fifth. Those are the 5 that we're going to find, right? We know the 8th term is 25. We know the 12th term is 41. How many common differences will we have between them? By not 3, but 4. Does everyone see that we have 4 common differences between those two numbers? So we could subtract and then divide. What is the last one? 41. The 8th one is 25. Divide that by 4 because 12, erase that. 12 minus 8 is 4. So what is 41 minus 25? 16 divided by 4. So what's our common difference? 4. That's another way. I'm not saying that one way is the wrong way or the best way or the fastest way or the easiest way. You decide how your brain works, right? But when I think of this as being linear, then I'm thinking of this as being kind of like slope, right? We said D was similar to M, y equals mx plus b. Our common difference is like that slope. That's the number that we're multiplying by whatever we're plugging in. So isn't this the change in y, kind of, and the change in x? So there's 2 ways of thinking about it. So far, so good? Okay. So we could write this whole pattern out like this, and we could now use our common difference of 4 to generate all of our terms, right? We could back it off and go forward or whatever. Or we can say that we can also realize that the 8th term is 25, right? So if the 8th term is 25, then 25 has to be equal to our common difference times 8 plus our C. Does that make sense? And what is 4 times 8? 32. So if we subtract 32 from both sides, what do we get? Makes sense that negative 7 could be C. Okay, so if negative 7 is C, that's our 0 term, right? Then what would our first term be? What would our second term be? And our third term? And our fourth term? And our fifth term. Now let's see if it's right. What would our sixth term be? And our seventh term? Eighth term? 25, right? And 25 plus 4 is plus 4, plus 4, plus 4. Okay? So figure out how your brain works and use what works for you. But we see about 3 different ways that we can do this problem. Make sense? Okay. Questions on this one? All right. So, next year I think I'm going to have an exploration so we actually, my next year's students will figure this out on their own, because I hate just telling people why this works or that this works. Okay? Too many times we just tell you, here's a formula, use it. And we don't ever get to figure it out on our own and explore it. But when we're talking about the sum of a finite arithmetic sequence, okay? In other words, we're finding the series for a finite arithmetic sequence. We're going to give you this formula that says if you want the sum of n terms, you take n divided by 2 times the quantity a1 plus a sub n. So n divided by 2 times the first plus the last. So far so good? Okay. So we have 2 last problems to work on. One of them is finding the sum of 40 plus 37 plus 34 plus blah 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 plus 25 plus 22. Now, is there a big gap between 34 and 25? Not really, right? So we can probably figure out how many terms there are between those two. Make sense? So do we have a common difference here? Negative 3. So our common difference is negative 3. So if we take away 3 from 34, we get, and when we take away 3 from 31, we get, and then take away 3, we get 25, right? So we know our common difference is a negative 3. And we know that we have 7 terms. So if we want the sum of 7 terms, we take 7 and divide it by 2 and take it times our first term plus our last term. So our first term is, last term is, 40 plus 22 is 62 divided by 2. 31 times 7. 31 times 7. There we go. I was hearing 270, and I'm like, 270 is not right. 217. I wasn't hearing it with a projector. All right, makes sense? Okay. Now, if we didn't know, if there was a big gap between those and we didn't have the time, like on an ACT or an SAT, to figure those out, right, then we could potentially do what? Okay, well, we could say We could add them up, but chances are when they give you an ACT or SAT, at least when I was in your seat and took that, they gave you some pretty big things to add up, pretty long sequences, and it's very easy to make a mistake, and it takes too much time. You only have 60 seconds per problem, right? So I would never suggest adding them up. Okay, but we know that our first term, our formula, or our common difference is -3, right? Okay, so could we write the explicit formula for this guy? A sub n would be -3, our common difference, times n, and what would be the term before the first? 43. Okay, so there's our explicit definition. Now we don't know for sure what term 22 is, right? Pretend, because we figured it out. But if we didn't know what that term number was, we could say, well, 22 is equal to -3 times some term number, I don't know what it is, plus 43, right? So what would we do to simplify this? Subtract 43 and divide by -3, and guess what we're going to get? 7, because there were 7 terms. So there's so many ways to work your way around this. That make sense? Okay, if there's too big of a gap and you can't fill in the gap to see how many terms you have, that's one way of doing it. All right, last example. So we talked about infinite arithmetic and geometric sequences, or infinite sequences, yesterday. And we said that they have that ellipsis at the end and they keep going on and on and on forever. Well, obviously, if you're continually adding numbers to an arithmetic sequence, you can never find the true sum of one that goes on and on and on forever. But we can ask you to find a partial sum. So we can give you a sequence and we can say, hey, I want to know what's the sum of the first 50 terms. Make sense? Okay, so if I want the sum of the first 50 terms, the minute you see that you're adding up 50 terms in an arithmetic sequence, you want to use your sum of a finite arithmetic sequence formula, because we're saying we want the first 50, even though it goes on and on and on forever. So we write our formula down. It's right above it. But it doesn't hurt to write it down, because practice makes perfect and you remember it, right? So I would recommend writing every one of them down every single time. So it's repetition. Okay, so we want the sum of 50 terms, right? So let's plug things in. We want the sum of 50. We know we have 50 terms. We're dividing it by 2. Do we have our first term? Do we know our last term? No. So we have 2 variables here. We can't do anything about it yet. So what can we do? If we find the explicit formula and then find the 50th term, we can sub it in, right? So what's the explicit formula going to look like? Yeah, dn plus c. What's our difference? 4. And what would our c be? -10. So now which term do we want? Because we said if we're subtracting, okay, so we want a sub 50. So we're going to take 4 times 50 minus 10, and we're going to get, so 190 is our 50th term, our last term. So far so good. Now it's just a matter of simplifying. -6 plus 90, 190, 180, 184, and 184 times 25. 4,600. going to make you think this chapter. But it's good for us. So far, so good? Any questions on this one? Okay, assignment.